Today I want to talk about expectation values or averages. Now, this is a concept that crops up quite often, both in quantum physics and classical physics, such as classical statistical mechanics. So this is just a formalization of what we understand by averages. So suppose we have some random variable x, and this random variable takes some values. So x can take the values from some set, which has the values x1, x2, x3, dot dot xn. In principle, this set can be a continuous set, and often, in fact, the example that we're going to do in class will have a continuous variable, but for the sake of discussion, we can take it to be a discrete variable. And now we have some probability distribution for this random variable. So we have some p of x, and the probability distribution is some set where we have p of x1, the probability that x will take the value x1. Let's use the shorthand small p1 for this. So p of x2 similarly would be, the shorthand would be, say, small p2, so on and so forth, until p of xn is small p of n. Now since these p's are probabilities, we can expect for the sum, so the sum goes from 1 to n, to give us 1. Now if this was not a normalizable probability, then this sum would not give us 1, and we can easily deal with that, and I'll mention this at the end of this lecture. Now suppose we have some function f of our random variable x, and we want to find out what is the expectation value or the average of this. So the definition of the average of this function f of x, sometimes denoted by these brackets, sometimes denoted in this way, it's given by the sum over f evaluated at the values of the random variable xi, multiplied or weighted by the probability pi. So this is our formula for the expectation value or the average. Now, in case the probability was not normalized, then we have the sum of the relative probabilities or unnormalized probabilities would be some number, say P, big P. Well, we have something called big P already, so let's not use that. Let's call it C. Then the average f of x would be given by the summation over all these cases. So the numerator stays the same, but in the denominator, we normalize it like so. So this is what it means to take an average. So let's look at an example. Suppose we have some game, and the game has 3 outcomes. So these outcomes are, say, we label them 1, 2, and 3. So this is going to be our random variable. And suppose that there's some probability distribution for these guys. So we have, say, p of the probability of 1 happening is, say, a half. Say, a probability of 2 happening is, say, 1/4. And the probability of 3 happening is 1/4. And suppose associated with each of these outcomes, we have some reward. Suppose it's some money, so we get the reward, say R, when you get 1, you get very, like only 1 unit of credits. But if you get the reward, if you get 2, then you get 5 units. And if you get 3, you get, say, 3 units. So then we want to find out what, like if I play this game over and over again, what is the average that I can expect from each of this game, each turn of this game, right? That is what the interpretation of the expectation value is. So we say R of X. So because, the probabilities are normalized, so we can just sum up the, R of Xi's, multiply them by the probabilities. Sorry, let me put Xi here. And then this is going to be 1 times half plus 5 times 1/4 plus 3 times 1/4. And this is half plus 5/4 plus 3/4. And so this is going to give me 4, 2 plus 5 plus 3. So I get, in the numerator, I get 3 plus 5 is 8, 10. And then in the denominator, I get 4. So my expectation value is 5/2 or 2.5. So if I keep on playing this game, on average, I will win 2.5 credits.